Hello everyone and welcome to my video series about sequences. Great. Now let's take a couple of videos and try to understand what a sequence is. The definition for a sequence is very simple. Basically, a sequence is an ordered list of elements, or you can think it as a ordered list of numbers. Okay. Now let's try to write an example. Now think about a collection of numbers. Okay. Let's try to think about a collection of numbers. What is the simplest collection of numbers you can think? Well, it's 1, 2, 3, 4, 5 and so on, right? Now, do they have a pattern? Yes. Are they ordered? Yes. Now let's put two curly brackets, and that's a sequence, a collection of numbers which they have a definite pattern and they are ordered. Okay. Now a definite pattern means that if you want to tell what's the thousandth term of the sequence, you can exactly say what is the thousandth term of the sequence, right? If you want to know the 10,000th term of the sequence, you can say exactly what is the 10,000th term of the sequence. Basically, sequence is just not a random collection of numbers. It's a collection of numbers which they have a ordering and a certain pattern. Okay, now in this video series we are only going to learn about infinite sequences, meaning there's infinitely many terms in the sequence. Okay, or in other words, in simple words, you cannot ever finish writing all the terms of the sequence. That's why I put 3 dots after this comma, because I don't want to write all the terms of the sequence, and which I cannot do. Okay, so we are only going to talk about infinite sequences where there's infinitely many terms of the sequence. Okay, let me write another example of a sequence. So 1, okay, my first term is 1 and 1/2, 1/3. Now you can guess the next term, right? 1/4. You can write the rest of the terms of the sequence, right? Okay, nice. This is another example of a sequence. But if you really look at these two sequences, it's a terrible notation, right? To represent a sequence, I have to explicitly write out few terms of the sequence. Now come on, we can do better than that. So that's what we are going to do. We are going to try to establish a better simple notation to represent sequences. Now to do that, we can go back to functions, because think about functions. Here's an example of a function, f(x) equal to 1 over x. What a simple notation. To represent functions, we have simple notation, right? This is how we represent a function, for example. For different inputs of x, we get different values of functions. Now when we are representing a function, we don't explicitly write out all the values of the function, right? This is how we represent a function. Now in functions, and well, actually in your calculus classes, you thought x as an independent variable usually, and x usually is a real number for you in your calculus class, right? Keep that in mind. A real number means you can have x to be a whole number, 1, 2, 3, 4, 5, or a fraction, a decimal, irrational number, whatever you like, right? Numbers like that. Now let's think about sequence. Let's try to come up with something like this for sequences. Now to do that, we are going to look at the position of terms of the sequence. Now look at the second sequence. Let's start with the second sequence. So the first term of the sequence, so that one represents the term. Okay, first term of the sequence is 1. Second term of the sequence is half. Now third term of the sequence is 1/3. Fourth term of the sequence is 1/3. Now you can clearly see there's a connection between the position of the sequence and its relevant term of the sequence. Now if you go back to the first example, first term of the sequence itself is 1, clear connection. Second term of the sequence is itself 2. Third term of the sequence is 3. Now you can see a clear connection. Now we are going to use that connection to write a general term of a sequence. Now remember, in the definition of the sequence, we said that sequence is an ordered list of numbers. Since it's an ordered list of numbers, we will be always we will be always able to make a connection between the position of the sequence and its terms. Okay, a clear connection. I mean, clear connection means you won't see it right away, but somehow if you spend enough time, you should be able to. Okay, not you will be, that's not guaranteed, right? But you should be, let's put it in that way. All right, now instead of using x, I'm going to use n to represent, okay, like sort of like the independent variable to represent sequences. Okay, so n, now n actually here, let's say that n represent the position of the sequence. Okay, so n can be only whole numbers 1 2 3 4 5, because you can't say like 5.1th position, right? So position cannot be decimal, position cannot be a fraction, right? Position cannot be an irrational number, right? It can be only be 1 2 3 4 5, right? So and so on, right? A whole number. Now if I want to write a general term for the first sequence, I can say it's n. Okay, just plain n. Okay, when you say n, when n is equal to 1, that means when you say when n is equal to 1, that means the first position. When n equal to 1 means first position, n equal to 3 means third position. Now the third position of the sequence is 3, fourth position of the sequence is 4. So this sequence itself is n, and we say this is, we can say a sub n is equal to n. Now what's this a sub n? Now a sub n is playing the same role like fx. So that's the notational. Okay, and n is actually the position of the sequence. Now this is not a very good example to see this. Now in the second example, I can say a sub n, this sequence is 1 over n, because when you say n is equal to 3, that means what is the third term of the sequence? What is the third term of the sequence? 1/3. What is the fourth term of the sequence? 1/4. So I can use the position and I can make a function using the position of the sequence. Okay, so that's the difference between sequences and general functions. Actually sequence is also in its own way a function. Okay, right, now the most important takeaway here is that n is the position of the sequence. We use the position of the sequence itself to write a general expression for any given sequence. Okay, now how to do that, we're going to learn that in the next video, some sort of a strategy to do that. Okay, but here just we are focusing on the notation. Now there's one more thing with the notation. People usually have a curly bracket around this expression. Okay, so here also I will have a curly bracket. Okay, now in this curly bracket, that's just to differentiate it from distinguish it from a regular function. Okay, and to give its own representation. Okay, for a sequence to give its own representation. And not only that, in this curly bracket, people usually put two numbers. Here I put 1 and infinity. Here also let's put 1 and infinity. What does this mean? Well, this means the range of the position of the sequence. That means you are n is going from 1 to infinity. That means the sequence is infinitely long. It is an infinite sequence. So it's starting, n values are starting from 1 and go until infinity. Okay, so these two numbers represent, this is the starting point. Okay, so let's say starting point of n, and infinity is not a number, so that's how far you go in the sequence. This is an infinite sequence. So that's the meaning of two numbers that you put. Okay, all right, now at this point let's look at exercise 1. Now here's what I want you to do. Look at those 5 sequences and write the first 3-4 terms of the sequence. So for example, let's take the first sequence. So this is how you represent the sequence. Let's try to write the first 5 terms of the sequence. What is the first term of the sequence? So if you want to find the first term of the sequence, substitute n to be 1, because 1 means that's the first position. So when n is equal to 1, 5 minus 2 is 3. So 3 is the first position. Now if you want to know the second term of the sequence, substitute 2 for n. So 5 times 2 is 10, 10 minus 2 is 8. That's the second term of the sequence. Now if you want to know the third term of the sequence, substitute 3 for n. Now 5 times 3 is 15, 15 minus 2 is 13. That's the third term of the sequence. Likewise, you can generate all the terms of the sequence by just using this general representation. Okay, now I'm not going to do all these 5 problems because they are easy enough for you to do. Okay, now here's what I want you to do apart from this. Just take these 5 sequences and try to draw them. Okay, draw them means in a minute, okay, I'm going to show you a Mathematica code. Now this is super important. Okay, try to visualize how a sequence look like, and that's also important. Now you have seen a lot of functions and you see how functions look like when I say e to the x, you know how, hopefully you know how e to the x looks like. Just like, try to get comfortable with sequences by plotting them. I'm going to show you a code, and you can find this code in my website, and link for my website will be on the description of this video. Okay, try to download that Mathematica code and try to plot several sequences, and I'm going to show you in a second how the code works. So let's go ahead and see how the code works. Alright, here's my Mathematica code for sequences. Now you feel free to download it, feel free to look at the codes and write them in your Mathematica, write them in a Mathematica file and try to play with this code. This code will be very handy when we go into the topics like convergence and divergence of a sequence. Okay, alright, so the first line is that you have to enter your sequence, the general representation of the sequence. So let me actually use a simple sequence 1 over n. This is the sequence that we discussed in the video, right? So you enter that, and then from the second command you can get the list of the terms of the sequence, actually first 10 terms. So if I hit enter, you can see these are the first 10 terms of the sequence. Now if you want more terms of the sequence, instead of 10 here, see, it's n is going from 1 to 10. You can put any number you like and see the terms of the sequence. And here's the most important thing. You should try to visualize the sequences that are given to you. Okay, so this is how the sequence look like, 1 over n sequence look like. That's very important. Just like we look at functions, graph of functions, it's very important to look at graph of sequences, graphical representation of a given sequence. Okay, so here's my suggestion. Whenever you see a sequence in your class, whenever you are learning about sequences, always try to plot it and see its behavior. It will help you with understanding convergence and divergence of a sequence later. Okay, alright, so here I can draw 50 terms of the sequence. If you can increase this number here and draw more terms of the sequence as well. Now this manipulate command means you can see the behavior of the sequence when you try to draw more and more terms of the sequence. See, I can increase this bar. Okay, that means you are drawing more and more terms of the sequence. Now you can see the behavior of the sequence, right? It's like a decreasing sequence, like, right? Of course it's decreasing, but you can understand certain things by looking at this manipulate graph or in Mathematica. And the other thing is, by using this command you can find the limit of the sequence. In this sequence 1 over n, the limit is 0, so that's handy too. So this code is very handy if you're going to learn about sequences. So feel free to download it or feel free to copy it and use it, play with it. That's something great that you can do. Okay, alright, we will be using this code in my future videos of this playlist. So I have explained this code a little bit. It's fairly a straightforward code, so then I can use this code in my future videos to explain stuff. Okay, alright, so I'll catch you up later.